Hi everyone, this is the first full video for astrophysics. This video will begin talking about the stages of stellar evolution for stars of various masses. We will discuss star birth, brown dwarfs, main sequence stars, and how they're able to keep producing energy. Keep in mind that there will still be a lot of details that won't be covered, but are still important to know. So I highly encourage you all to further research this topic on your own. I want to start by going over some important terms or concepts for understanding stellar evolution. To start, you might hear me mention solar mass a lot, or see this symbol. This simply means the mass of the sun. Other objects in space are often measured in comparison to the sun. This circular symbol here signifies the sun, so you might see it like this. This will just refer to the luminosity of the sun, or in other words, solar luminosity. Also, we will be looking at at life tracks, which are also called evolutionary tracks. These basically show the path that the star will take on the HR diagram as it evolves over its life. They're very useful in understanding how a star's surface temperature and luminosity changes throughout each stage of their life. We'll be looking at several of these in this video. Lastly, if you're at least somewhat familiar with the periodic table of elements, isotopes, and the structure of an atom, I think you'll have an easier time understanding all of these concepts. You might be wondering why we differentiate between stellar evolution for low mass and high mass stars. The reason is because a star's evolution is determined primarily by its mass. More specifically, the lifetime of a star decreases rapidly for increasing mass. In other words, massive stars do everything faster. This chart here shows how much the mass of a star affects its main sequence lifetime. So here, 30 solar masses have a main sequence lifetime of about 10 to the 7 years, compared to 10 to the 10 years for 2 or 3 solar masses. This diagram shows the distribution of stars in the universe in terms of mass. As you can see, low mass stars are actually far more abundant, and very high mass stars are actually relatively rare. The life of a star begins in cold, dense molecular clouds in the interstellar medium, or ISM for short. ISM is just what we call the space between the stars and is composed of gas, dust, and other kinds of particles. The clouds that stars are born in are mostly composed of H2, or molecular hydrogen. Its own gravity will begin to push the cloud into itself, making it contract and increasing the temperature. This is because the gravitational potential energy is converted into thermal energy and radiative energy. As the cloud contracts, the outward gas pressure is increasing. This clump of gas is now considered a protostar at this stage. These protostars are still relatively cool and dark. Therefore, if you take a look at this life track of a star, it makes sense that the protostar can be found in the lower right corner. When it gets to the point where the gravitational contraction and internal pressure is balanced, it is considered to have reached hydrostatic or gravitational equilibrium. Now the star is considered a pre-main sequence star, or PMS star. Eventually, when the temperature of the core is high enough, around 10 million Kelvin, nuclear fusion will start to occur, more specifically hydrogen fusion. It has reached the main sequence of the HR diagram, and a star is born. It is now called a zero-age main sequence star, or ZAMS star. It remains in this stage for most of its life. If you remember from the last video, this is the stage that our sun is currently in. This particular evolutionary track is for stars with the mass of our sun. This next chart shows the life tracks of various masses from 0.5 solar masses to 15. You can clearly see how much faster the higher mass protostars go through each stage. Around 150 million years for 0.5 solar mass stars compared to just 60,000 for stars of 15 solar masses. The massive stars will end up being larger and hotter main sequence stars. The opposite is true for less massive stars. For protostars that have masses below 0.08 solar masses, something else happens. Due to its low mass, it will not reach a high enough temperature for nuclear fusion to occur. Therefore, they never truly become a star, since they've never been powered by nuclear fusion. These are called brown dwarfs, and sometimes referred to as a failed star. They actually resemble big planets more than stars. These are very cool and dim, so it's very difficult to observe them. Now, what exactly is nuclear fusion or hydrogen fusion? Nuclear fusion is a star's source of energy. At this stage in a star's life, what's going on is that hydrogen atoms are fusing together to form helium. One way to think about it is that helium is like the ash left over from burning the hydrogen. I should mention that whenever I use the term burn when talking about stars, I really mean nuclear fusion. But for simpler understanding, it's useful to think of it sort of in that way. Anyways, we will talk about two possibilities for this to occur: the proton-proton chain and the CNO cycle. For stars less than 1.5 times the mass of the Sun, hydrogen will commonly be transformed into helium via the proton-proton chain. During this time, the star will get gradually bigger, hotter, and brighter. Let's take a look at what the proton-proton chain reaction is. The proton-proton chain is a process for fusing hydrogen into helium. In case you didn't know, hydrogen is an element that has a nucleus containing one proton, and helium has a nucleus that contains two protons and two neutrons. An important condition for this reaction to occur is extremely high temperatures. This is because since protons are positively charged, they naturally repel away from other protons. This is known as the Coulomb barrier. The way to overcome this problem is to have a very hot environment, which will make the protons travel at really large velocities. This will allow the protons to collide with each other. So the first step is for two protons to collide and fuse together to form deuterium, which is an isotope of hydrogen that consists of one proton and one neutron. This reaction will also produce a positron and a neutrino. A positron is basically a positively charged electron. The positron will quickly find an electron and will create two gamma rays. In step 2, the deuterium will combine with another proton, and that will produce helium-3, which consists of two protons and one neutron. There will also be some gamma rays produced. The time from step 1 and step 2 is extremely brief, only around 4 seconds. The final step involves the collision of two helium-3 nuclei. This will produce a helium-4 nucleus, which was what we were looking for, and two protons. This can be summarized with this equation. 6 protons and 2 electrons were involved in this process. It will create a helium nucleus and two protons, making a net loss of 4 protons. Other products include neutrinos and gamma rays. Lastly, the mass of the reactants is slightly more than the products. The mass loss is converted into energy using the famous equation E equals mc squared. For stars greater than around 1.5 solar masses, they will commonly produce energy through the carbon-nitrogen-oxygen cycle, or CNO cycle for short. As a reminder, this process is a process for fusing hydrogen into helium. It is much quicker than the proton-proton chain, though. The carbon, nitrogen, and oxygen suggested by the name are actually used as catalysts for this reaction and aren't used up in the process. You'll see what I mean in a moment. Let's start with carbon-12. If we combine with a proton, it will create nitrogen-13 and also a gamma ray. Because nitrogen-13 is unstable, it will undergo beta decay, which will produce carbon-13, a positron, and a neutrino. Just like in the proton-proton chain, the positron will quickly find an electron to produce two gamma rays. This carbon-13 will then combine with another proton to form nitrogen-14 and also a gamma ray. Nitrogen-14 will be combined with the third proton to yield oxygen-15 and a gamma ray. Once again, because oxygen-15 is unstable, it will undergo beta decay, which and then we'll end up with nitrogen-15, a positron, and a neutrino. As you may guess, the positron will pair with an electron to form two additional gamma rays. Lastly, nitrogen-15 will combine with a fourth proton to create a helium-4 nucleus, which is our end goal, as well as carbon-12, which is what we started with. And this cycle will continue. Do you see how this is a cycle that doesn't use up the carbon, nitrogen, and oxygen elements, and how they are simply catalysts for converting hydrogen into helium? Hope that made sense to you. This equation here should summarize this process. From 4 protons and 2 electrons, we were able to end up with a helium nucleus. We also ended up with neutrinos and gamma rays, just like in the proton-proton chain. And because of the mass difference between the left side and the right side, the mass loss will be converted into energy described by E equals mc squared. I think this is a good time to talk a bit about the solar thermostat. So how does the sun control any large rises or falls in temperature? It's quite simple, actually. Let's start with a drop in temperature. If the temperature isn't as high, then fusion will also slow down, right? Then that will lower the internal pressure, pushing out of the star, and that creates an imbalance so that the pressure pushing in increases. That will cause the core to contract and heat up, which will restore fusion back to normal. Similarly, if the temperature of a star increases, fusion will correspondingly increase. The core's internal pressure will then be greater than the pressure coming in. The core will then expand, cool down since it's farther away from the core, and then we're back where we started. It's a pretty neat concept to prevent any drastic changes. Anyways, back to the main sequence. The main sequence phase ends after the supply of hydrogen in the star's core is almost depleted, and it enters the subgiant stage. Now the star's energy supply will come from the gravitational contraction of the star again. The core will begin to cool, which will cause the outer layers of the star to weigh down on the core. This causes the core to heat up again, which will begin the nuclear fusion of the thin shell of hydrogen around the helium core. These pictures show what the thin shell would look like. This is called shell hydrogen burning. Then the core contracts again, which will increase the radius of the star and decrease its temperature. This might seem counterintuitive to you because if the core is shrinking, how does the star get bigger? Recall the solar thermostat. As the core shrinks, it is becoming denser and hotter, which increases the rate at which fusion is occurring. From there will be an increase in the energy flowing from its core, which will expand the star's outer layers. The star can expand to several times its original size, which will cool the outer layers, which is again expected from the solar thermostat. The star is now a red giant, which is the upper right corner of the HR diagram. It will move up the red giant branch, or RGB, on the HR diagram. There will be also a lot of mass loss in a stellar wind due to the weaker surface gravity. From here, it will steadily increase in temperature again as its helium core contracts. And just like when the star had a hydrogen core, the helium in the core now will undergo fusion via something called the triple alpha process to form carbon and oxygen. The triple alpha process gets its name because it involves 3 helium nuclei, also known as alpha particles. So the goal is to take those 3 helium nuclei and get carbon plus some energy. The first step is that 2 helium nuclei combine to form beryllium. Beryllium-8 is unstable, so another proton must quickly combine with it to form carbon-12 and a gamma ray. As with the rest of the nuclear fusion reactions that we've talked about, energy is also released here. At this point in the process, if the conditions are right, carbon-12 can also combine with another helium nucleus to form oxygen-16, which is a stable isotope and a gamma ray. Okay, and that would be it for this video. We will continue with the other stages of stellar evolution in the next video, so make sure to check that out. If you have any questions, you're always welcome to contact me, and stay safe.